Semiconductors are the unsung heroes of the modern world. These tiny electronic components power everything from smartphones and laptops to cars and spacecraft. Without semiconductors, our lives would be drastically different. But what exactly are semiconductors and how are they made? The journey from raw materials to sophisticated microchips is a fascinating one involving cutting-edge science and engineering. It all starts with something surprisingly ordinary: sand. This abundant natural resource provides the basis for silicon, the most common semiconductor material. In this essay, we will delve into the intricate world of semiconductor manufacturing, exploring the key processes and highlighting their significance in our technology-driven society. The transformation from sand to silicon is a multi-stage process that requires immense heat and precision. First, the raw silicon dioxide found in sand is extracted and purified to an extremely high degree. This purified silicon dioxide then undergoes a chemical reaction in a furnace, where it is heated with carbon at incredibly high temperatures. This process converts the silicon dioxide into pure silicon, which is then further refined to remove any remaining impurities. The resulting material, known as electronic-grade silicon, is incredibly pure, with only one foreign atom for every billion silicon atoms. This level of purity is crucial for the subsequent stages of semiconductor manufacturing. The next step involves growing large, cylindrical crystals of this purified silicon, which will eventually be sliced into thin wafers. These wafers serve as the foundation upon which integrated circuits, the heart of microchips, are built. While pure silicon is a semiconductor, its conductivity is limited. To enhance its electrical properties, a process called doping is employed. Doping involves introducing a small number of impurity atoms into the silicon crystal lattice. These impurities, called dopants, can either donate or accept electrons, altering the availability of charge carriers within the silicon. This controlled introduction of impurities allows engineers to fine-tune the conductivity of silicon, creating regions with different electrical characteristics. There are two types of doping, N-type and P-type. In N-type doping, impurities like phosphorus or arsenic are added, which donate extra electrons, increasing the material's conductivity. P-type doping, on the other hand, involves adding impurities like boron or gallium, which create holes by accepting electrons. These holes act as positive charge carriers, enhancing conductivity in a different way. The magic of semiconductors truly comes alive with the creation of transistors, the fundamental building blocks of modern electronics. Transistors are miniature electronic switches that can control the flow of electricity with incredible speed and precision. By combining N-type and P-type doped silicon regions in specific configurations, engineers create transistors that can amplify signals, switch currents on and off, and perform logical operations. These tiny switches are the foundation of all digital circuits, from simple logic gates to complex microprocessors. A typical transistor consists of three terminals: a source, a drain, and a gate. The flow of current between the source and drain is controlled by a voltage applied to the gate terminal. The ability to control electrical current in this way revolutionized electronics, enabling the development of smaller, faster, and more efficient devices that have transformed our world. The next stage in semiconductor manufacturing involves building complex integrated circuits on the silicon wafers. An integrated circuit, or microchip, is a collection of millions or even billions of transistors, resistors, capacitors, and other electronic components interconnected on a single chip. The process begins with a process called photolithography, which uses light to transfer intricate circuit patterns onto the silicon wafer. A photosensitive material called photoresist is applied to the wafer and then exposed to ultraviolet light through a mask containing the desired circuit design. The exposed areas of photoresist harden, while the unexposed areas remain soluble and can be washed away, leaving behind a patterned layer on the wafer. This process is repeated multiple times with different masks and etching steps to create the intricate layers of an integrated circuit. Once the circuit patterns are etched onto the wafer, layers of conducting and insulating materials are deposited and patterned to connect the various components, forming the complete integrated circuit. Semiconductor manufacturing is an incredibly precise and delicate process requiring meticulous control over every aspect of the fabrication environment. Even the tiniest dust particle or impurity can ruin an entire batch of chips. To maintain this level of cleanliness, microchip fabrication takes place in specialized clean rooms. These controlled environments are designed to minimize the presence of airborne particles and contaminants. Clean rooms are classified based on the number and size of particles allowed per cubic meter of air. The cleanest clean rooms used in semiconductor manufacturing have particle counts far lower than even the most sterile hospital operating rooms. Workers in clean rooms wear special suits, gloves, and masks to prevent contamination from skin cells, hair, and other particles. The air inside a clean room is constantly filtered and circulated to remove any airborne contaminants. The impact of semiconductors on our world is profound and far-reaching. These tiny electronic components are the driving force behind the digital revolution, enabling the development of countless technologies that have transformed the way we live, work, and interact with the world. From the smartphones in our pockets to the computers on our desks, from the cars we drive to the medical devices that save lives, semiconductors are everywhere. They power our communication networks, enable scientific discoveries, and drive innovation across industries. The global semiconductor industry is a massive and complex ecosystem involving companies from around the world that specialize in various aspects of chip design, manufacturing, and distribution. The demand for semiconductors continues to grow at an unprecedented rate, driven by the proliferation of smart devices, the rise of artificial intelligence, and the increasing digitalization of our world. As we look to the future, the importance of semiconductors will only continue to grow. Advances in semiconductor technology are paving the way for even smaller, faster, and more powerful devices. Researchers are exploring new materials and fabrication techniques to push the limits of Moore's law, which states that the number of transistors on a chip doubles approximately every 2 years. Quantum computing, a revolutionary technology that harnesses the principles of quantum mechanics to perform computations, is also heavily reliant on advanced semiconductor materials and fabrication techniques. The future of semiconductors is bright, and these tiny electronic components will undoubtedly continue to play a pivotal role in shaping the technological landscape for generations to come.